like for y'all to welcome Mr. Rick Fowler.
Thank you, Jeff. I appreciate the introduction. I'm excited to be here today and talk to you about Delta House. Delta House, strange, try that. Just a second. Delta House was in fact named after the Animal House movie. We have, our geologists are very creative, and they named some of their prospects after Animal House characters like Marmalade and Bluto and Otis. And so we subsequently decided to call the facility that we flow back to Delta House, which we do have a creative bunch over at LLOG. I thought some of y'all may not be as familiar with LLOG as others, and so I thought I'd just very quickly go over LLOG. We've been around since 1977. We are a private company. In fact, we are the largest U.S. private oil producer. And this surprises a lot of people. We're fifth most active Deepwater Gulf of Mexico driller. If you look at the last 5 years, who's drilled the most wells, we're actually fifth in the Deepwater Gulf of Mexico. We've done 21 deepwater projects to date, and we've got 42 wells that we brought on production. We've got 2 floating production systems. Houdat has 10 wells on production. Delta House is what we're talking about today. We've got 8 wells on production there. Delta House is producing over 100,000 barrels of oil equivalent per day. So I like to start by just giving you an idea of the size and scope of the project. And so I like to start with this picture that shows the facility in relation to something that you might understand the size of. That is an apartment complex to the right there. So this is not where Delta House sits today. This was during its tow out. It goes through Aransas Pass, and you see that is a pool by that apartment complex. And oops, sorry, that pool there. And I like to imagine myself by that pool drinking a nice Corona, a little lime in it, and then all of a sudden the sun gets blocked out, and I'm like, what is that? I assume it's a cloud, but you kind of look up and see this behemoth floating by. Just to give you an idea, that's about a little over 2 acres footprint of the facility, so it's pretty good size, about 19 stories tall. So just some general information about it. It is called a 4-column semi-submersible. First production came on in April of this year. Total project cost is about $2 billion. That includes the first 7 wells drilled and completed, the subsea systems, the exports, the floating production system, the installation, everything. The peaking capacity is 100,000 barrels a day and 240 million cubic feet per day. We know right now of 5 fields that will produce back. Ultimately, we think there'll be more fields. When we started construction, we only knew about 3 of those fields. The water depth is about 1 mile deep, and it is designed to withstand a hurricane, a 1,000-year hurricane. So what is unique about this project relative to other floating production systems in the Gulf of Mexico? This one we designed to be the first of many. And in fact, we are currently adjusting that design to consider building it again. We began engineering prior to any discoveries. That's very unlike every other project. Every other project, typically they get a discovery, and they'll do a pre-feed study, a feed study, then a full-blown detailed engineering, and then they'll go out for bid. We actually started engineering before we had any discoveries, and in fact, we actually bid the yards before we had any discoveries so that they could have input and they could help us tell them how it would be easier for them to construct. We do have private equity owning the floating production system and exports. I'll talk about that briefly. We sanctioned the project with only 2 wells drilled, 1 in each of 2 different fields. That's pretty amazing. Typically, most operators will have usually on the order of 4 wells in a single field before they would start construction on a facility like this. Because of the creative financing we did, we lowered our threshold where we could comfortably go forward with just the 2 wells drilled. And then I think most importantly, about 3 years from discovery to first production. Typical deep water projects take about 8 years to get to first production. So let's talk about just some numbers. 39,000 ton displacement, 15 megawatts power generation. That is a lot of power generation. Over 12,000 people were involved. And I know we think of crude oil but I think sometimes it helps to convert that to gasoline. This would make enough oil and gas to make about 1.5 million gallons of gasoline per day. So I'd like to start with just describing the overall system and what it's designed to do. So the wells are these little, there we go, little trees. So these would be the individual wells. They flow back through these green lines to our floating production system, which that's what we'll be talking about mostly today. So a couple things to be clear on. First, we don't drill from our floating production system. The wells are located at least 3 miles away from our floating production system. And really the purpose of the floating production system, when oil and gas is produced out of the ground, it's never nice, clean oil ready to go into a pipeline. Unfortunately, you always get a mixture of oil, gas, and water combined. If you tried to put that in a pipeline and send it 53 miles to the shelf, in this case, it would never make it. It wouldn't flow that far. And so the purpose of this facility is really to do two things. One, it separates the oil from the gas from the water, so we can put the oil in an oil pipeline and the gas in a gas pipeline. And then the second thing it does is increase the pressure. Generally, we don't have enough pressure to get all the way to the shelf, and in fact, with oil, we have to reduce the pressure to get all the gas out of it, and then we have to pump it back up at a pressure high enough for it to get all the way to the shelf, where it'll ultimately arrive at a refinery and end up as gasoline. So there is a facility, as I mentioned, it is designed for a 1,000-year storm. In fact, in a 1,000-year storm, the wave height will not hit that truss. That's that horizontal section. And that truss is designed for full impact, so this is considered a very robust system. This particular one is designed to go anywhere out to 10,000-foot water depth. So it is held in place. Instead of anchors, we use what's called suction piles. These are suction piles. They're about 16 foot in diameter, about 85 foot long. We use 12 of them, 3 on each column. So the way these work, it's like you can think of it as a can with a top on it. We pump the water out. Since it's strong enough not to collapse, the only thing that can happen is it has to suck itself into the seafloor, and then it has chains on it. I'll show you the chains in a second, and that's what hold this thing in place. But those are, a very solid way to hold our facility in place. This is the construction process for making these suction piles, and you wouldn't think inch thick steel can bend, but here you have 2 rollers offset. And as we put the steel to those rollers, it does in fact bend inch-thick steel. So here are the chains. Each chain length, this is not like bicycle chain, each chain length is about 3 foot tall and weighs over 500 pounds. So that would be one link. So you can kind of see where the people are in the background and get an idea of the size of these. The chain, a lot of people think, well, gee, the chain is the kind of dumb iron, right? It's not that exciting. Actually, there's only a few places in the world that can manufacture this chain. The specs are very tight. A typical spec on a chain is -0 to +1 millimeter. If you think about it, if it was smaller than it was supposed to be, it wouldn't give you the strength you want. And if it was a little thicker than you wanted it to be, you're adding a lot of weight from all these different chain links added together that would take away payload from your facility. And so the specs on that are very tight. And of course, the manufacturing, the tricky part is you got to manufacture one link while it's connected to another link. And you got to make sure your heating process does not affect the link next to it. Industry has had a couple of failures in chains, and so we work very hard on this chain. And so just to give you an idea of what the chain looks like in place, there we go. That would be the chain right there. So you can see each one of those links we saw on the previous page. That's how they show up on the actual facility. Okay, we don't use chain all the way from the seafloor to the FPS. That would add up way too much weight. And so instead we use ropes. It's polyester rope. This rope was manufactured in Belgium. It is about 10-inch diameter, and on that reel that you see there, it's about 10-inch diameter. And it's quite strong. And the other thing that's nice about it is it's designed to be neutrally buoyant. In other words, it's the same weight as seawater. So if you're in 1,500 foot or 10,000 foot of water, that rope doesn't actually add any weight. It is neutrally buoyant. Okay, so now I'm going to zoom in on the wells. We'll show you that in a little bit more detail. So we'll start with the subsea tree. These you're probably familiar with from some of the Macondo public, media publications. But you can see there's a lot of connections there where ROVs can stab in these sections right here, where an ROV can go in and turn those valves manually, but we can also control them from the floating production system. This is our manifold. Manifold is what allows flow from the wells to be directed to either of the two flow lines. So once again, these green flow lines are what connect to our FPS. The flow would come from the wells into the manifold, and we can direct each well to one of these lines. There's an advantage to doing that. We could have one line designated as oil, sometimes one line designated gas. If we have gas wells, you might have one line designated as high pressure, a different line designated as low pressure, but it helps to be able to control which well flows into which line. These are also, you can daisy chain these to have multiple 4-slot manifolds. This is a 4-slot manifold. You could put 4 wells on it, but you could hook 2 of these together and get 8 wells. And then we have the flow line end termination, and that connects the end of the flow line to the flow line itself. And so here's the flow line, and this would be your flow line end termination. And then one thing I'll point out, you notice there's a hub sticking up on this, and also on the manifolds we had hubs sticking up, and then on the tree you have a hub sticking up. And so the way these get connected together is after they're put on the seafloor, we send down an ROV, a remote operated vehicle, to exactly measure the distance between those 2 hubs. Then we'll specifically manufacture a jumper, and here's a picture of a jumper. And then we'll pick this up and put it in place, and then it has latches that lock it in place and maintain our pressure stability. All our equipment in this particular field's designed for 10,000 PSI of pressure. So here's the ROV, in this case, looking at the subsea tree. And so you can imagine how all this gets put in place. And that happens very quickly. It's typically within a couple of days we'll get the jumpers installed. So we do have to control the wells, and we also want to pump chemicals to the wells. Those chemicals would include wax inhibitors, asphaltene inhibitors, hydrate inhibitors, which we generally use methanol. And so we have these series of tubes that we wrap together, and we call that an umbilical. And so this is the umbilical, and so this would be a cross-section of the umbilical. And those tubes, once again, they would inject chemicals. Sometimes they do just hydraulic fluid that we use to control with pressure. We can control certain valves. And then, of course, we also have electric. These are, we typically have 2 quads on an umbilical. That would give us both signal and power, which we'll use power to turn valves off and on at the wells. So that's pretty important. And then with this particular setup, we also have, I don't know if you can see that, but that would be a fiber optic cable. Fiber optic is faster. Sometimes in this field, for example, wells are 14 miles away from our facility. We have to demonstrate that we can shut in the well within a certain period of time, which is a matter of seconds. And so to be able to get that signal to the well sooner, even though you wouldn't think that the light is that much faster than electricity, it does help to achieve our required specifications on shutting in a well. Then we have our pipelines. So this on the upper left is line pipe, that's 16-inch line pipe for our gas export line that was manufactured in Germany. The upper right is a special pipe that goes from the seafloor up to the FPS. If you can imagine our FPS, it does float. It's a floating production system. So it does bob a little bit and moves. If you can imagine, that piece of pipe will move with the facility. And so we have to worry about fatigue, which if you imagine a tin can bending it back and forth, it would eventually get a crack. It's the same type of situation here where that pipe has to be very specifically designed to resist that fatigue motion. And it turned out there was only one place in the world that would be able to meet our specifications on this steel catenary. It's called steel catenary riser, is that specific piece of pipe. And there was only one place in the world that would meet those specs, and it's in Wakayama, Japan. So this is some of that pipe. And here they are on the lower right, extruding that pipe. You can think of that like your old Play-Doh system where you would squeeze the lever and it would form various shapes that would squeeze out the other side. So that's how they manufacture this pipe. And then when we install it, this would be a typical vessel. Oops, excuse me. that we use to install it. These big reels, we would weld these stalks together till they're about a mile long, and then we reel them up on this reel. Sorry about that. This mouse is messing with me here. We reel it up on that reel, and then it comes back over, and that's how we would lay the pipe. And we can lay about 7 miles, get 7 miles on these reels on this particular vessel. It's called the Deep Blue by Technip as the owner of that vessel. So they did most of our installation work. Now, when we lay the pipe, we do have to connect. We pre-lay all the pipe before the floating production system gets there, and it's all laid on the seafloor, and then we pick it up off the seafloor and hand it to the FPS. And that is a little more tricky than I just described. And so I would like to spend just a minute on that operation because we did something unique on this operation. So first, let me describe these are called riser adapters. And down here, we have a specific piece of pipe that will fit into that adapter. And we designed this actually on our last project. And so we can put in any size riser insert to accommodate anything from about 2 inches up to about 24 inches with our riser adapters. But pulling those in is very tricky. If you can imagine a big vessel handling this very heavy piece of pipe right next to another big vessel, the FPS, and making sure those don't run into each other, that is a very difficult, challenging operation. And keep in mind, they're both moving up and down, and so the weather constraints can be quite challenging. One thing we noticed with our facility is that the deck is inset from this is called the ring pontoon, and there's about a 12-degree angle from the edge of this deck to where these riser adapters are. That 12-degree angle, turns out that's about our departure angle that we want that steel catenary riser to depart where it departs the FPS and heads towards the sea floor. And so that made installation pretty nice. So I got a little video here of what we did there as we took advantage of that. And different, in this case, we're using 10 different risers. And so with each one, they want to have a different departure angle so they don't bounce against each other. And so what we'll do is actually list the floating production system to direct a particular riser into its riser adapter, and then we'll list it a different way for the next riser. Most people, when we first described that to them, they thought we were nuts to intentionally list our facility, but it worked beautifully, and let me show you the video here. So here we are, and it's showing the heel and the trim that we're going to list the facility to for a particular riser. Each of those flow lines coming up would have been a riser, and then we have 2 export risers. So we've already installed 8 this way. So that is called a turn-down sheave, and that turn-down sheave connects, this is a riser adapter. It pulls down, and that'll connect all the way to where the pipe is. So the pipe was previously being supported by the pipe lay vessel, and now it's being handed over to that winch via that turn-down sheave. And that turn-down sheave can be placed anywhere on the deck. So now the FPS has the weight of that pipe. We send down an ROV to cut a sacrificial grommet. Then we're using that winch to pull in. And once we've pulled it in, then we can start doing some very fine adjustments with the FPS. And so this is a computer model. In a minute, it'll show you the actual images from where we were lining up the riser with that riser adapter slot. But you can imagine, you can see we're trimming, very slight trim adjustments to get it perfect. And there's an actual image, and you can see it looks just like the computer model, which was, I think, pretty fascinating. I think it was also exciting that the way these typically are installed, they'll use divers down there. They'll use a series of winches that have cables underwater and use a series of them to try and get them to line up exactly. If you can imagine divers between these 2 big vessels, that is, once again, a more challenging operation, involves some safety. We never had to jump divers for this installation, but more importantly, we could work in much rougher weather. Typically, a window is less than 3-foot seas to do this operation. We worked up to 9-foot seas with 40 mile per hour winds to do this operation. We saved about 2 weeks of schedule doing this compared to a more typical riser installation. So that listing, we ended up, the maximum list was about 5.5 degrees. I happened to go to Italy this summer, and I did go to a town called Pisa. And I happened to notice that that 5.5-degree angle was pretty similar to my Delta House 5.5-degree angle. And as you can see, I was very excited about when I realized that, so I was jumping up and down. But that's, it is a little discerning, you know, disturbing when you first see your facility listing, but it is a very controlled situation, and we actually had several backup plans in place. But that was a pretty exciting aspect of the project. Let's talk about the construction. The hull was built at HHI's yard in Ulsan, Korea. In the upper left, that crane you see there, that's called a gantry crane. That is the largest crane in the world, 1,600 tons, Guinness World Book of Records. When we were building it, there was another vessel in the dry dock. You build this in a dry dock. Basically, you pump all the water out of an area and put a wall there, pump the water out, and that's where you build. And then when you're done building, you remove the wall, water comes back in, and it floats out. So that's a dry dock operation. So here we are in the dry dock, but there was some other activity in the dry dock that interfered with our assembly. And as a result, we had to assemble very fast. And if you look at the dates of these, so the upper right is December 9th, and the lower right's January 2nd. So that's less than a month. You can see how much construction was done. I think this really speaks to the quality of HHI's yard. I can tell you I've worked at a lot of different fab yards around the world. A lot of times when you put two big pieces next to each other, which they had assembled these pieces, laid them all around the yard, and then they brought them in once we were able to assemble our unit. When you put those two big pieces next to each other, a lot of times they won't exactly fit. They'll be as much as an inch off, and then you have to use pry bars, if you will, and welding to try and get everything to fit up just right. In this case, everything fit. Everything fit just right the first time, and so they were able to assemble it extremely quickly. In fact, we laid steel March 4th, 2013 for the hull was our first cutting of steel. They were ready in March of 2014. So it's about a year from first cutting steel to sail away on the hull, which is pretty amazing. So to bring it over to the United States, like I said, it was built in Korea. We put it on the back of what's called a heavy lift transport vessel. That vessel you see there is the Dockwise Treasure. We can ballast that vessel down to where it's that deck that it sits, that the FPS the hull is sitting on, is below water, and then the hull can actually just float on board, and that's exactly how we did that. Which to me was you can see how calm this water is. It was almost like a little pond, but we were in a bay there in Korea, in Goji, Korea. To manufacture the topside was built at Kiewit Yard in Ingleside, Texas, just outside of Corpus Christi. So we manufactured the truss, as shown in the upper left, and then the main deck on the bottom left. And then you use a series of these cranes. You can see those cranes have tractor treads on them. They all lift together and move over. This is the largest. That's called a float over, and this was the largest float over that Kiewit had ever done. Which it's a big single deck, which is a big advantage, we think, to our type of unit relative to some other units. Most units you see in the Gulf of Mexico have 3 decks, and the issue with 3 decks is that you can't float over the second deck till all the main equipment's there on the first deck, and so if there's a delay in one of those pieces of equipment, you really have to wait. Whereas with our single deck, if there's a delay in one piece of equipment, we can always reach it with a crane later. So here's the topsides fully built. I'll point out to you that it was built on a couple of rails. These are the rails right here. Those are the 2 rails. And so when we get ready to install it, we extend those rails out onto a barge, use a series of cables to pull it on the barge, and that is, once we get it on the barge, so here it is being pulled out onto a barge, then we move that barge under the heavy lift device. It lifts up, put the hull under, and it goes off. And it goes just that fast. It's really amazing. That is the largest lift Kiewit had ever done. This one was 9,580 tons. So that is a pretty big lift, which they've done, I believe, now 24 of the lifts for Gulf of Mexico facilities. So after we get the top on, we tow it out to place. We use a series of 7 tugs to get it through Aransas Pass, which that's what that picture I showed you earlier next to that condo. Okay, so that's pretty much the project. So let's just a couple of common questions. One, why did we choose this design instead of some other design? I'm sure if y'all are familiar with Deepwater, y'all are familiar with some of the other options out there. We do like wet trees. We like our drilling operations separate from our production operations. Those are very different operations. And if there's a well event, we don't want it to affect our production. If there's a production event, we don't want it to affect our wells. So that is different than a number of other operators. We had just executed HUDAT, so this was a very similar design. You can see HUDAT pictured in the lower right. This is about 50% bigger than HUDAT. I talked earlier about how it's flexible to 10,000 foot. One of the main things I want to mention, though, is the quayside integration. So if you compare this, for example, to a spar you have to upright in deep water, and so then you have to do that lift of the top sides in deep water. That is the riskiest part of this project, and I'd much rather do that in a controlled environment, quayside, and I don't have to do it on a particular day when there's only 3 vessels in the world that can do that lift, and if I don't use them today, they're going to be not available for another 3 months. So quayside integration, I think, greatly reduces the risk of the project. And we talked earlier about the single deck. And then reduced steel, so that's pretty interesting too. So we specifically designed this hull to be as efficient as possible, meaning I can get the most payload for the minimum amount of steel. And in fact, if you look at on this particular unit, of the ratio of the payload of the top sides to the weight of the hull, it's a 1-to-1 ratio. That is unheard of. Most typical is 1.2 to 1.5. So having a 1-to-1, I'm using less steel, and so it's less costly to fabricate. We talked earlier about how we started the design before we had a discovery. How could we even do that? Well, you got to put together a couple pieces of information. First, LLOG had 15 of what we call hub class prospects at that time. A hub class meaning if it's successful, it would likely be a new floating production system would be the development type. Also, our historic exploration success had been 70% in the Gulf of Mexico. And so you put those two together, and we might expect to build 10 units. And you can imagine most companies do one at a time. Everything's custom built. If we knew we were going to do 10 of these, we want to get really good at doing these. And so the way to do that is to do a very similar design over and over again. And so by doing that, we gave up some custom ability, right? You can't do 10 custom and get the same benefits as doing one standard design. So one of the things we looked at, and that's what the chart shows, is how accurate are we as an industry at designing these facilities, at predicting what the rates are. And so what that shows on the x-axis there is the design rate in thousands of barrels of oil per day for oil facilities compared to the actual peak utilization. That is, at the time, that was 42 deepwater floating production systems in the Gulf of Mexico, which if we had designed each of these exactly right, you would have no points below that line. So if you designed for 50,000 barrels a day, typically that meant the field could do a little more than that, say 55 or 60, and you have a little flat life. And so the fact that a lot of these were below their design, they never produced below their design, means that we really aren't that good at predicting rates. And in fact, if you look at a couple of the real big ones there, those were substantially less than their design rates. The other thing that's interesting about this curve is you see a couple of points that are significantly above the line. And what that means is that so for example, this point here, that facility was designed for 100,000 barrels a day, but it actually flowed 150,000 barrels a day. What that means is they did a debottlenecking operation on it, and we were able to get it to produce more than their original nameplate. And we recognize that as a possibility at Delta House. So given all that, we felt it was more prudent to go with a standard design, which would handle a wide range of fluids. We can handle anything from 28 to 38 degree API gravity oil. Beyond that, if we got some oil, let's say, that was below 28, we could still flow it. It just wouldn't get 80,000 barrels a day. It'd have longer retention times, for example. Another unique aspect of Delta House was the infrastructure financing. In this case, we had a private equity firm out of Boston named ArcLight, and they provided the capital for the floating production system and the export lines. And that reduced the capital that the producers had to pay, in this case LLOG. LLOG's not 100% of this project, We have a number of producers involved. But that reduced the capital that the producers would have to pay by about $860 million. And by doing that, that greatly changed our economics and allowed us to go forward with the project sooner than we otherwise would have. So the graph in the lower left shows the present value versus number of scenarios. At that time, we considered a self-build where we funded ourselves. The ArcLight case, which was the deal we ultimately did, flowing back to existing units, which there was no single unit that we could have tied back to that had enough capacity. We'd have had multiple projects to handle these multiple fields. It would have been very complex. And the last line on the curve, which these are, by the way, actual slides from our 2012 partner meeting when we were deciding what to do. But at that time, we ran a low price sensitivity of $75 a barrel. That's kind of an interesting statement there. But you can see the P profile versus reserves doesn't change that much. But if you look at the rate of return on the right versus reserves, you've really increased your rate of return, especially at the low end of the reserves range. And in fact, that greatly reduced our threshold to where we'd be comfortable going forward with the amount of reserves we had identified at that time. Most companies, given the 2 wells we had, would have drilled more wells probably before they even starting to design the facility. And it would have been much longer than the 3 years it took us to get to first production. So here is just a little more on the timeline. Like I said, we started engineering and bidding the yards before we had our discovery. Our first discovery was February, which was SOB2. That one was never really a hub class prospect. Our first hub class discovery was in May of 2012. And so we truly were a little bit less than 3 years from our first hub class discovery. Started topsides in December. As I mentioned earlier, we started the hull in March. It takes about 60 days for that hull to come from Korea to get to the United States, and so that happened in 2014. We did that integration where we lifted the topsides in June, which I got to tell you, when that thing's lifted up and there's nothing under it, I have to hold my breath. It is incredible to see that 10,000 tons just suspended in midair. And we got first oil production in April. I'll show this. This is just a chart showing the time to first production for all the Gulf of Mexico floating production systems. And you see the 2 log projects there towards the bottom, and Delta House was just 3 years. And so you can see that more typical is 8 to 10 years for a floating production system. So Delta House going forward in 3 years, I think, is an amazing accomplishment. A little bit more future plans. We are, like I said, we have 8 wells on production. We're currently drilling number 9. We'll have a total of 11 on production by this time next year. So we're doing a lot of activities at Delta House. In fact, we're looking at a debottlenecking study there. In addition to that, we are beginning engineering for our next floating production system. So we're taking the lessons learned from this model and applying it. It's going to be a number of small changes. It's not going to be a complete redesign. It's just a number of small improvements. And those generally around increasing flexibility and increasing payload. And then we're going to drill exploration wells. Right now, LLOG has 3 deepwater rigs running. We expect to have at least two running for the foreseeable future. We'll have 5 hub class prospects we drill over the next 2 years. And because of that, we expect to put in another unit in my career, I hope, very soon. I do have a little video I'd like to show you, and then I'll be glad to answer any questions. So this is the project video we showed at the christening. We did bust a bottle of champagne on the hull back in July.
In 2012, LLOG Exploration drilled deeper than 3 miles beneath Earth's surface in the Mississippi Canyon area of the Gulf of Mexico, discovering oil in multiple fields in the region. With these discoveries, a means to process the production was needed to make it suitable for pipelines to transport the oil and gas to shore. As a result, later that same year, the decision was made to build the Delta House floating production system. LLOG carefully planned the Delta House project and emphasized improvement of safety to protect people and the environment. Delta House will provide a platform that is about an acre in size, located approximately 53 miles from the Gulf Coast of Louisiana, moored in a water depth of 4,500 feet. At its peak capacity, Delta House will process enough oil and gas to make 1.5 million gallons of gasoline per day, with enough energy left over to light up 80 million 60-watt light bulbs. Unlike most deepwater developments of its type, Delta House will have gone from discovery to first production in less than 3 years. Also unlike those projects, we're not about to make a boring video.
You know you make me wanna kick my heels up and throw my hands up and throw my hands back and come on now. Don't forget to say you will. Don't forget to say yeah. Say you will. Say it right now, baby. Say you will. Come on. Say
I like to show how many people, people don't realize how widespread one of these projects is. Literally 15 countries around the world, thousands of jobs. You can see quite a few of them right here in Louisiana. So it's a pretty exciting project. But with that, I'll be glad to answer any questions.
Hey, Rick, very impressive presentation. Obviously, the interesting facts is, being privately owned and time to first production and the amount of work involved. And I might be incorrect, it reminds me of the movie Dead Poet Society with Robin Williams when he had Carpe Diem, it seize the day. Certainly it's amazing, very impressive. I guess with that, the few questions I have, I'm just curious how much movement there is in a 24-hour period, and then with the next development, what are the I won't say disappointments, but things that
Sure.
you may change. And then lastly, what were the hurdles with Bessie as far as production was concerned?
Okay. Let me start with the movement. So with any of these deepwater facilities, they do need float. This is called a taut mooring system, which most of the facilities out there would use a similar mooring system. So the enemy of this particular design, it's called a semi-submersible, the enemy of this design is heave. It's an upward and downward motion. So for instance, in comparison with a spar, which is more like a cylinder, that's enemy is pitch. So this one does a heave, this one does more pitch, which one of the reasons why we chose this design, we could go with that flat deck with a lot of heave, but you can't do a flat deck with a lot of pitch because then your production fluids are flowing down one side of the platform, pitches the other way, it goes the other way. Even a few degrees, if you're a couple 100 feet long, can make a big difference where you're flowing uphill or downhill. So a typical heave would be a fraction of the wave height. So you can, if it's a calm day, it's not going to move much at all. But most days, I'll say, when you're on the facility, you can tell it moves. Now, if you're not paying attention, it won't necessarily feel like you're moving. But so if you're in a pretty rough seas, let's say 10-foot seas, you might get a couple of foot heave. Would be about all you would feel. And the pitch is very slight on this unit, whereas on been on spars where it's been about 5 degrees. So it's been a bit more. So that's that question. You said the regulatory issues with Bessie. Bessie, we work very closely with Bessie and Coast Guard. DNV was our classification agent, and they work on behalf of the Coast Guard to basically check every calculation that's been done to make sure this thing is safe and has the characteristics that it says it's supposed to have. And so, for instance, we do wave tank testing, we do computer modeling, we do all that stuff well before we start building. So, biggest hurdle, Bessie, in my opinion, has been very good to work with. They've done a number of inspections. They fly out unannounced, and we've had first several visits, we had no inks. We've had one ink now. It's very minor ink for documentation, but no incidents of noncompliance. But during the construction phase, I would say the challenges were more on the Coast Guard end. They have some preferences that aren't detailed in the regulations, and so we had to make sure we understood all those preferences. And I apologize, I forgot your third question.
Disappointments or big
Oh, big disappointments. Okay, so let me get the presentation back up here. When we shipped on that vessel from Korea, we did not tie down the chains tight enough, and as a result, we had some damage to our fair leads. That was, I think, probably the single biggest whoopsie, which if that's the biggest whoopsie, life is good. Let me get to that picture again. It's pretty far back there. There we go. Okay, so you can see the chains here were a little loose. And so if you can imagine, which is perfectly calm here, I can tell you that the ride from Korea to the United States was not perfectly calm. That ship was rocking. And as a result, those chains moved up and down, and these fair lead, these are called fair lead brackets. These round things are the fair leads, fair lead brackets. So those chains would just rub up and down against the fair lead brackets, and it sawed through them like butter. They had 2-inch thick gouges in them. So we will definitely design a tighter system there when we transport next time. We were able to repair that damage in a couple of weeks, but if it was a little worse, it could have been much worse. But that was probably the single biggest learning. We will build in some extra flexibility onto the next unit, and that's what we're working on now, is to get some extra flexibility. One of the things we'd like that we didn't have on Delta House is the ability to do water injection, so we will design that into the next unit. Any other questions?
I guess one last one, Marcondo, I don't know, where are y'all operationally in that field, and will that well, where will it flow once done, what facility, if it's successful?
So, Macondo. So we don't, just to be clear, LLOG does not own the Macondo well or the 2 relief wells. We did buy a portion of the Mississippi Canyon 252 lease. That being said, I'm not really able to talk about details of specific fields. Sorry.
I have 2 questions. Thank you for the presentation. It was very informative. First question is, what is the estimated lifespan of the OptiX model? And the second question is, the current state of the industry slowing down or delaying engineering or cutting of steel of the expected projects that come for the hub class?
Okay. Our design life for Delta House is 20 years. That being said, typically a lot of deepwater facilities, they have a design life and they've gone beyond that design life. And the typical reason, which when you design everything for a certain design life, you make sure that's good and then you stop. If during production it turns out that you need more time, you start doing, and it's typically that fatigue analysis I talked about. So this thing does move, and if you can imagine the interaction between the deck and the various equipments and some of those structural components, you have to demonstrate that those can all meet that fatigue criteria. And typically, if it doesn't, you can add some welds and do different techniques to extend the life beyond the original design life, which in this case is 20 years. Most units use sacrificial anodes for corrosion protection, where you might see these on the sides of spars and that sort of thing. This one uses an impressed, let me get back to, there we go. So this one would use an impressed current system. So we actually put a current through the hole, and that's how we manage corrosion. So with some other type of design, you might have to install new sacrificial anodes, which this one, since it's current impressed, generally that's not an issue. So that is the design life. Is the current pricing environment affecting deepwater projects? Absolutely. A number of projects have been announced as canceled or slowed down. Not at LLOG. We don't have any floating production systems that have, or any discoveries that need floating production systems right at the moment. If we did, we would probably go forward. As a private funded company, we can behave a bit differently than than public companies. We are, in fact, going forward with our engineering of the next Delta house, even though we don't have a discovery yet. So we are moving forward. Industry as a whole, it is more difficult to go forward on this type of project. As you can imagine, you have to find more reserves for the same. If the cost is going to be the same, you got to find more reserves at a lower price in order to make the economics work. In this case, our cost of this floating production system is about 2/3 of what an independence cost is, and it's probably 1/3 of what a major's cost would be for this type of unit. So in sometimes where other companies struggle to make a project work with their economics and the way they've always done it, we can come in with a faster schedule and a lower cost and perhaps help other operators get to first production on a project that was struggling using their typical methods. If you can imagine something that costs 3 times as much and takes 8 years instead of 3, those economics are going to be a lot worse than what we would be able to do. And so we're typically able to work forward with a much lower price environment.